Okay, I think we are ready to start the day with Nick's third lecture. Nick, are you ready?
Yes, I am.
Then let's go.
Great. Thank you again for showing up. Welcome to day 4, my third lecture. Last time we finished up our discussion of supersymmetric quantum mechanics. We had a gauged version of that A-type quantum mechanics I talked about on my first lecture. We had an n=4 version where we had a Kähler target. And then I introduced some 3-dimensional supersymmetry algebras, or well, a 3D supersymmetry algebra, the 3D n=4 supersymmetry algebra. The super translation part of the algebra takes the form I wrote out here. A flurry of indices. I hope you can forgive me. Here's a little reminder of what each of these bits are. A dot alpha, B dot beta. Those are all plus or minus. They correspond to SU2 fundamental indices. The SU2 that rotates A and B is sometimes called SU2H, or for Higgs. There is another SU2 that I'll call SU2C that rotates the dotted indices. Those combine to give us an SO4, which is identified with the R symmetry that rotates the supercharges amongst themselves, but doesn't touch space-time at all. And then there's also the alpha and beta indices that are also SU2 indices. And the corresponding SU2 I'm calling SU2 sub E, corresponding to Euclidean rotations. This is the spin group of my 3-dimensional space-time. Mu and nu are going to be the vector indices of the spin group. And this sigma, mu, alpha, beta is the intertwiner that takes 2 spinners and gives you a vector, the Pauli matrices, if you prefer that name. And then we talked a bit about topological twisting and twists in general. I mentioned that there are 3 types of twists up to rotations of space-time and R-symmetry rotations. And they take this rough form. There's a twist that's mixed, holomorphic, topological. And there's 2 topological twists, A and B. And I wanted to mention that there's a particularly important subalgebra that we're going to be talking about later that includes the A-type supercharge. And I've denoted it like this. We can imagine in this A-type supercharge I wrote up here, having also the minus dot showing up there. And that gives us 2 supercharges. And then we can also look at the difference of the 2. So that's what happens here. Sigma 3 is the matrix 1, 0, 0, minus 1. And together, this QA and Q tilde A give us 4 supercharges that commute only to translations in the time direction, which I'm calling U=3. And as we'll see later, the 3D n=4 supersymmetric gauge theories we're going to be interested in will be able to be written in terms of, or written as one of the n=4, one-dimensional n=4 algebra or theories that we talked about last time. And so my aim is to show you what the result of that reduction is and explain how we can get vortices out of that reduction. Okay, so with that reminder out of the way, I wanted to give you some of the basic building blocks that go into describing a very common class of supersymmetric gauge theories in 3 dimensions, some 3D n=4 gauged linear sigma models. So let's start out with some nomenclature. Last time I mentioned that we often collect fields that transform into one another under supersymmetry into so-called supermultiplets. And I wanted to tell you the 2 basic supermultiplets that are going to go into building the 3D n=4 theories that we're going to talk about today. and also tomorrow. So there are two basic building blocks, or well, two, maybe you could say four. But the first one is what's called a hypermultiplet. This is, roughly speaking, how our matter fields are going to be organized. It's got two types of fields. There are some bosonic fields that I'm going to call Z. These are going to be, well, let me write out some indices for you. They're going to have two indices. There's going to be a lowercase a, that's this SU2 Higgs index. And then there's an uppercase A that runs from 1 up to 2 times n. You can think of these as maps from our 3-dimensional space-time to, maybe I'll say C to the 2n. You can kind of think of this as a hyperkähler space, and this A index is some sort of like symplectic index, if you will. In addition to these bosonic fields, there are also some fermionic fields. Again, I'm going to abuse my ability to use indices. I'm going to call them psi. They have an A dot index, this SU2 Coulomb index. They're also going to have a capital A index, the same one that we have up here. And they're going to be spinors on space-time. So they're going to transform in the fundamental representation of SU2E, of SU2C, and then it'll also transform as sort of a symplectic thing with this A index. The second type of building block that we're going to have is what's called a vector multiplet. And vector multiplets are also in 3-dimensional n=2 field theories. So to distinguish the type of vector multiplet we have, I'm going to call it an n=4 vector multiplet. This is where our gauge fields are going to live, vector multiplet. So the bosonic fields well, I told you that the gauge field is going to live here. So there's my gauge field. The connection on a principal bundle. And there's also a collection of scalar fields. They've got Coulomb branch indices. There's 2 of them, and they're symmetrized. So in some sense, this is in the adjoint representation of that SU2C. And it's going to be valued in the adjoint representation of the Gaugely algebra. And then also there's some fermions. I'm going to call them lambda. And there's also a flurry of indices here. A dot alpha. It transforms in the fundamental representation of SU2 Higgs, Coulomb, and Euclidean rotations. So it's a spinor on space-time, and it transforms as a bispinor of the R symmetry. Also called a vector of SO4. Okay, so these are the 2 basic building blocks. And the type of 3D n=4 theory we're going to consider where the vector multiplet is in some compact, corresponds to some compact Lie group G. So that means if I denote by frac G the Lie algebra of G, then this scalar field phi is going to transform in the adjoint representation of G. This field lambda, this fermionic field, is also going to transform in the adjoint representation of G. And our gauge field is going to be a connection on a principal G bundle on spacetime. And the hypermultiplets are going to be valued in general, it's some sort of pseudo-real representation. So A is going to be some sort of symplectic thing. G is going to have some homomorphism into the symplectic group that rotates this A index. And we're going to take the simplest type of pseudo-real representation. I'm going to call the full thing R. And it's going to be a direct sum of a unitary representation non-cal R and its conjugate. So when I do this, this choice of splitting of our representation R, what I'm going to have is this ZA field is going to break up into a matrix that I'll write like this. There's going to be a field X that's going to be valued in R. There's going to be a field Y that's valued in R dual. And then we have the complex conjugate fields Y and X bar, Y bar and X bar. They're going to fill out this matrix. So this A index, this SU2 Higgs index, is going to rotate the columns. So X and Y bar, they're both valued in this representation R, and they'll be rotated amongst one another by SU2 Higgs. And same thing with Y and X bar. They're both valued in R dual, and they're rotated into one another by SU2 Higgs. There's also, I guess I should say, there are twisted versions of these. Namely, there are so-called twisted hypermultiplets and twisted vector multiplets, where we effectively apply that mirror automorphism I was talking about last time. So you take these multiplets I wrote down here, and you exchange the SU2 Higgs and the SU2 Coulomb indices. We're not going to worry about them all that much, but I should mention that you can build theories with them. We just won't do that here. These theories have two types of flavor symmetries. That are going to act on our fields. The first type is called a Higgs branch flavor symmetry. I'll mention what the Higgs branch is later. I'm going to call it G sub H. And it fits into an exact sequence of the form G. Well, I said that it was some subgroup of the unitary representation, or of the unitary group that rotates R. In some sense, by doing the splitting, I've taken the unitary symplectic rotations and split it into just two copies of the unitary representations that are sort of off diagonal, or sorry, diagonal with a negative on the bottom. So G is a subgroup here, and the Higgs branch flavor symmetry group is the quotient of the unitary rotations on R that are independent of G. The second type of flavor symmetry is called a Coulomb branch flavor symmetry. And I'm going to call the group G sub C. It's a little bit more subtle, and I don't have time to really give it the justice it deserves, but at least the simplest version of it is given as follows. It's given by the Pontryagin dual of the fundamental group of G. So if your gauge group G is like U1, then GC is going to be U1, pi1 of G is Z, and homomorphisms from Z into U1 is a group U1. And more generally, it tells you that if you have some number of abelian factors, you're going to have that number of abelian factors inside of the Coulomb branch flavor symmetry group. And roughly speaking, GC measures the topological type of the gauge bundle sourced by certain operators. As a reminder, this pi1 of G is the thing that measures the topological type, or topological type of G bundles on spheres is measured by pi1 of G, and this GC is just the Pontryagin dual of that measure. Okay, great. So just as we said last time, it's possible to turn on background fields when you have flavor symmetries. The Higgs branch flavor symmetry couples to vector multiplets. So if I want to couple to a Higgs branch flavor symmetry, I'll couple to some kind of vector multiplet valued in a subgroup of GH. And a Coulomb branch flavor symmetry transforms or is coupled to a twisted vector multiplet. So this is where those twisted versions come in. And just as we said last time, when you have these flavor symmetries, you can turn on background fields for them. We have these scalars phi a dot, or sorry, a dot b dot. And turning on background fields can include turning on background values for those scalar fields, so-called twisted masses, as we saw last time. So just for some nomenclature, if we turn on a background vector multiplet for GH, the scalar fields phi, or the background values of those, are going to be a triplet that's going to be rotated by SU2 Coulomb. I'm going to denote them M. And just as we saw last time, these are going to be required to lie in some specific Cartan subalgebra if we want to support or preserve the Higgs branch flavor symmetry, or sorry, if we want to preserve supersymmetry. So I choose some Cartan torus of my group G. This is going to be the Lie algebra of it. Maybe I'll make it a frac T. And there's going to be 3 masses because this is each A and B can take 2 values and it's symmetric, so there's 3 of them. And then a background twisted vector multiplet for the Coulomb branch flavor symmetry will lead to a set of twisted masses that I'm going to call T, AB. This is why I had to call that a frac T. But it's valued in the Cartan torus of our Coulomb branch flavor symmetry. And there's 3 of them, just as there are with the masses. Just for context, these guys are called mass parameters, and these guys are called phi A Iliopolis parameters, or just for short, Fi. Okay. Cool. I'm not going to write down the action for these theories because ain't nobody got time for that. if you want to see what they are, then you can take the 3D or the 1D n equals 4 theories I talked about last time, although I guess I didn't give you the action for those either. And the version of these theories reduced to 1 dimension that I'm going to explain later will give you the action if you're sufficiently strong. If you really want to see it, then I can tell you afterwards, but like I said, it's kind of a mess. One thing I will tell you is that the zero energy field configurations have a nice description in terms of the geometry of these spaces. In particular, if we look at the classical vacua, the first thing that we see is that the phi's all commute amongst themselves. One thing I will do, just to make my life a little bit easier, like here, I split up my hypermultiplet field into x's and y's and their conjugates. I'm going to take this triplet and split it up into 3 fields that I'm going to conveniently denote sigma, which is going to be a real scalar. And then the other 2 components are going to combine into 2 complex scalars that I'm going to call phi and phi bar. So this thing written in that language would say that sigma commutes with phi, sigma commutes with phi bar, and phi bar commute with one another. That's one of the classical vacuum equations. In addition, there are some equations involving both the scalars in the vector multiplet and the scalars in the hypermultiplet. And here we have a real mass parameter, which is the exact same splitting I've done here for phi, but now on that mass m over there. So it's going to turn into a real mass parameter mr. And the vacuum equation says the action of this Lie algebra valued thing acting on x is 0. And similarly, the action on y is going to be 0. This is analogous to the equation we saw in 1 dimension, where we had the real scalar of the 1D vector multiplet acting on our Riemannian manifold required we lie at fixed points. This is just the 3-dimensional analog of that statement. And then we also have the complex version of these. So we have the complex scalar phi, and then the complex component of the mass parameter m, that I'm going to call m sub c, and the action on x has to vanish. Similarly for y, there's also the complex conjugate version of these equations, but I'm not going to write them down because there are cooler things to say. And then the third class of vacuum equations say that the real moment map plus the real fi parameter equals 0. So I was saying that this is some sort of hyperkähler thing. This G action on R is going to be some hyperkähler type action. So there's going to be 3 moment maps that I'm going to collect just as these guys into a real component and a complex component. This is the real version of the equation. And again, the fi parameter is going to split up into 3 parts. There's going to be a real part I'm going to call T sub r, a real fi. And then there's going to be a complex analog u plus Tc equals 0. Okay, so solutions to these equations are going to correspond to classical vacua of this 3D n equals 4 theory. And we should identify vacua that differ by action of the gauge group G. And I want to specify or point out 2 important subspaces. So if the real mass and the complex mass vanish, then we can set our complex scalars phi and sigma to 0. And this first equation is satisfied, and the second equation is, sorry, the first and second equations are satisfied automatically. And then we just have this equation at the bottom, modulo gauge. So we have a special subspace, the so-called Higgs branch, that corresponds to solutions to this bottom two equations modulo the action of the gauge group. Yeah, it's an action of G on this cotangent type representation space. So the complex moment map kind of looks like X with Y outer product, if you will. And then the real moment map is like X outer product X bar and Y outer product Y bar. And you might recognize these as a hyperkähler quotient. So we have the representation R specified at our central value G, and this Higgs branch is realized as a hyperkähler quotient of our representation R. And this thing is called the Higgs branch. The SU2 Higgs flavor symmetry is going to act on the Higgs branch. This is a hyperkähler space, and it'll act by hyperkähler isometries of the Higgs branch. In particular, it'll rotate the P1 of complex structures. And here I've sort of chosen a specific complex structure by doing this splitting. The Higgs branch flavor symmetry we have over there is going to naturally act on this thing by hyperkähler isometries, but they're not going to rotate the complex structures. In a similar fashion, if TR and TC vanish, we have no FI parameters. We can set X and Y to 0. And then we automatically satisfy the bottom sets of equations. We still have the first one. The first one says that they can all be rotated into the same torus, Cartan subalgebra. There we're just going to choose some Cartan subalgebra of G, and we can rotate all of these fields into that same one. So that first equation says that sigma and phi bar can be thought of as elements in the torus of our gauge group that I'm going to call T sub G. And there's 3 copies of it. Doing this breaks the gauge group. In particular, I can't do arbitrary G rotations anymore. I still have rotations by our torus G. And one fun fact about abelian gauge theories in 3 dimensions is that the gauge field can be dualized to a scalar field that I'm going to call gamma. And this is going to be another free parameter on this branch of vacua, sometimes called a dual photon. This is a general feature of 3-dimensional gauge theories. This isn't 3D n equals 4 necessarily. And then putting these guys together, we have our 3 scalar fields that were in the vector multiplet, as well as this dual photon. And this describes the so-called classical Coulomb branch, which can be identified with 3 copies of our Cartan torus and a rank G number of circles, it turns out that because this isn't just an arbitrary two form, this is actually got quantized periods. The dual photon has to be periodic, which is why we have an S1. And this is then identified with C times C star to the rank of our group G, or T star C star, the rank of G. So this is also a hyperkähler space. This 3D n equals 4 supersymmetry dictates that these vacuum moduli spaces are hyperkähler. And just as with the Higgs branch, the Coulomb branch, R symmetry SU2C acts by rotating the complex structure. The Coulomb branch flavor symmetries act by hyperkähler isometries. Yeah. Oh, yes. Yes, great. I totally forgot. Thank you so much. So this should be mod the Weyl group, mod the Weyl group. So with respect to our Cartan torus T sub G, we have a Weyl group that I'm calling W, and the remaining gauge transformations that are around after we've brought everything to the Cartan torus still acts, and we have to quotient by the action of that. Oh yeah, I was gonna say that after I had a drink. So I didn't write classical on this Higgs branch. Turns out that this Higgs branch doesn't receive quantum corrections, which is a very deep theorem and a physics theorem, I guess. But this Coulomb branch, I did write classical. And that's because it receives very, very severe quantum corrections. And it's very difficult to describe the full quantum geometry of the Higgs or of the Coulomb branch. And only recently, like in the last 5 or 6 years, oh wow, it's been more, 7 years, has a description of this Coulomb branch been described in its full generality, or at least in some reasonable generality. You might have heard of these so-called Braverman-Finkelberg-Nakajima construction, and it involves the affine Grassmannian and very hard geometry. And that hard geometry reflects the fact that these quantum corrections are quite severe. But this is what it looks like classically. If I've got time tomorrow, or maybe later today, I'll tell you what it looks like. But for the moment, I'll leave it like that. Okay, so as I was mentioning in the first lecture and earlier today, our next order of business will be to write down this theory as a one-dimensional n equals 4 quantum mechanical theory. In particular, if we want to get vortex equations out at the end of the day, we're going to want to reduce this theory in a way that the 1D n equals 4 quantum mechanical symmetry group, or sorry, 1D n equals 4 supersymmetry algebra I wrote down before, this one generated by Q A dot A and Q tilde A dot A. We want to reduce this 3D n equals 4 theory in a way that makes manifest an action of this 1D subalgebra of the 3D n equals 4 supersymmetry algebra. So the next order of business is going to do that reduction, or at least to tell you the result. And what I mean by reduce in this context is not pretend my fields are independent of the other two directions, but instead view this set of fields as maps from our real line, which is quote unquote time, into fields on C in some sense. So for the hypermultiplets, I'm going to be lazy here and only tell you how the scalar fields get reduced. But we view the fields x and y bar. These guys are both valued in the representation R. Instead of being maps from R3 into R, we view them as maps from the real timeline into maps from some R2 into our representation space R. So this is some hugely infinite dimensional target space for our quantum mechanical theory. But we'll see that the supersymmetric ground states have a nicer description than this hugely infinite dimensional space. And we can do the same thing with the remaining part of the hypermultiplet scalars. They're also going to be valued in maps from C or R2 into the dual representation. We can do the same thing with the vector multiplets. The time component of my gauge field, together with the scalar fields, sigma, phi, and phi bar, are going to go into 1D n equals 4 vector multiplet. Namely, last time I only told you about the vanilla version of a 1D n equals 4 quantum mechanics where we didn't have any gauge fields. But of course, we can do a gauged version of that. And the bosonic fields of that gauge supermultiplet in 1D is going to contain a gauge field A and then 3 scalar fields that can be nicely organized like that. The covariant derivatives, dz and dz bar, organize themselves into a 1D adjoint valued field. And by adjoint here, what I really mean is that from the one-dimensional perspective, the gauge group is much larger than just G. Here, the gauge group is roughly going to be the group of gauge transformations from C into our original gauge group. So G is going to be, this now calligraphic G, is going to roughly be the group of maps from R2 into our original gauge group G. This is a point of distinction. Some of the other lecturers have been calling the gauge group this full group of maps from R3 into our target space. A physicist would not call that the gauge group. A physicist would call this thing the gauge group, and they would call this the group of gauge transformations. So from a 1D perspective, this thing is the gauge group. And the group of gauge transformations is going to roughly be maps from RT into this calligraphic G. And by adjoint here, I mean that they're valued in the Lie algebra of this calligraphic G. All right, so that's the first bit of the reduction. That's just telling you how the fields get reduced. The other bit of data that goes into defining these 1D n equals 4 theories is this superpotential W I was telling you about last time. And computing what the superpotential is not entirely difficult, but I don't have time to tell you exactly how it works. But what it looks like is an integral over the, maybe I'll call it dx squared. over the real plane R2. This is sort of like a sum over the indices of my very large representation, this thing, of y covariant derivative x. And as we saw last time, our supersymmetric vacua are going to be realized as critical points of this superpotential. So let's compute what those critical points are. So if we take the variation of this superpotential with respect to the three fields, inside of here is where our connection one form AZ bar is sitting. One thing I should mention is that instead of just thinking this as R2, I'm really thinking of this as some complex space C. I already sort of illustrated that by having Z's here. But anyways, the critical points of this superpotential, there are three equations that describe these critical points. The first one, if we take a variation with respect to y, says that the covariant derivative of x is 0. It's covariantly constant or covariantly holomorphic in the plane. The second equation we get by varying x, by integration by parts, we take this covariant derivative and slap it on y. And it too is covariantly constant or covariantly holomorphic in the plane. And then the third equation we get by varying with respect to AZ bar says that the complex moment map is going to vanish. Namely, if I take my covariantly holomorphic sections x and y, plug them into the complex moment map for the G action on my representation R, this is then going to be some coadjoint valued map from C into, some coadjoint valued map from C, and that's going to have to equal 0. Or if we had some Fi parameters, it would be equal to the Fi parameter. Okay, so these are my first three equations. We've got another equation that comes as the so-called D term equation. Last time I mentioned that the equations imposed by looking at the critical points of W are sometimes called F term equations. In addition to that F term equation, we have one other equation for the vacua. And it looks as follows. It says that, well, last time we said that it was the moment map, the real moment map is equal to 0. DZ and DZ bar are adjoint valued things, and the corresponding moment map is just the commutator of those two fields. That's just the moment map acting on the adjoint representation. And then we have the real moment map acting on our fields x and y, and that equals 0. You can think of this as, of course, the curvature of our connection in the z plane. And so this looks very close to our vortex equations. We have our covariant holomorphicity of our quote unquote Higgs fields. And we have something that relates the curvature of our field to the moment map of our Higgs fields. So this equation plus those three over there are what I'll call the generalized vortex equations. At long last, we finally see vortices. Sorry, it took so long. Of course, this is like a hyperkähler version of the usual vortex equations. I have the three moment map constraints. I have a complex moment map in its conjugate, as well as that real moment map. Those should be thought of as the three hyperkähler moment maps acting on this space of matter fields. And then we also have the covariant constancy or holomorphicity of our fields. So these are not so far from the vortex equations we've been seeing in other lectures. So what's the punchline of all of this? If we want to write our three-dimensional theory as an effective one-dimensional theory, our expectation is that we're going to get a one-dimensional theory with n equals 4 supersymmetry, and the target is going to be the solutions of these equations. So it's going to be the moduli space M of solutions to these equations. So we have A, Z bar, X, and Y, as well as their conjugate fields, such that del W equals 0, as well as our real moment map constraint, which we think of as a hyperkähler quotient, or sorry, just a regular symplectic quotient with respect to our gauge group G, cal G. And we've seen some Kobayashi-Hitchin type things in other lectures. And of course, this is some hugely infinite dimensional version of it, but it's, if you might call, a conjecture for you to try to prove that there is such a Kobayashi-Hitchin correspondence that says instead of taking a symplectic quotient by our group G, we can take instead a usual quotient by a complexification of our gauge group G. Of course, there's subtleties in terms of stability conditions, and that's going to go into very hard analysis of proving such a Kobayashi-Hitchin correspondence. But again, I'm just giving you work to do so that you can have a career. Okay, well, I'm at the end of my time. So I probably should be a diligent person and stop here. Next time, I hope to explain how to take these 1D n equals 4 theories with this moduli space of generalized vortices and somehow pull out a category from my pocket. But that's the plan.
Great. Are there any questions?
Can you hear me?
I can hear you, yeah.
So this
Yeah, so the generalized vortex equations are morally just a hyperkähler version of the vortex equations we've been seeing in the other lectures. So the usual vortex equations have some statement about the curvature and the moment map equaling 0, together with some holomorphicity constraint on our Higgs fields. In this case, our Higgs fields are actually some hyperkähler sort of thing. We have X and Y that are complex symplectic in some sense. So in addition to that real moment map constraint, we have a complex moment map constraint. So in the sense that the usual vortex equations say you have a Higgs field that satisfies curvature, or you have a Higgs field and a gauge field that satisfy a moment map equaling curvature constraint, together with a statement about covariant holomorphicity of our Higgs field, this is just a hyperkähler version of that statement, where in addition to that real moment map constraint, I also have a complex moment map constraint, it's conjugate, but still have this covariant constancy, or sorry, covariant holomorphicity statement as well. So that's what I mean by a generalized vortex equation. Yeah, that's totally, yeah. Yeah, exactly. Yeah, of course. So I've got a non-calligraphic G bundle on the plane, R2. You can also do this on surfaces, but I'm going to be lazy and just do on plane. So we've got a G bundle on the plane with connection A. I've got sections X and Y of an associated R and R dual bundle. And the vortex equations say that my section is covariantly constant. It satisfies this complex moment map constraint. And it also has the usual vortex equation that relates the curvature of my gauge field to the real moment map of my section. Yeah, exactly. They're unitary representations of non-calligraphic G. Yeah, of course. Are there any other questions? Oh, I would defer to the expert analysts in the audience. I by no means claim an understanding of existence of these solutions, although I'll provide an algebraic description of these moduli spaces next time. In particular, what we'll do is after this Kobayashi-Hitchin correspondence, we have a complexified gauge group. We're going to choose a holomorphic frame where AZ bar equals 0. And then we can say that X and Y are just actually constant, or sorry, actually holomorphic, and then do some algebraic version of this discussion where I have two holomorphic sections of a holomorphic G bundle on the plane that satisfy this complex moment map constraint, modulo holomorphic gauge transformations. And after a suitable algebraic rephrasing of that statement, I'll show you what some solutions look like. Or at least that's the hope.
And Nick, I think you forgot your vortex equation in M.
Which one?
Didn't you forget the vortex equation in the first line?
No, this is a double slash.
Oh, sorry, yes.
It's a symplectic quotient.
Great. Okay, if there are no further questions, then we can close the lecture here.